happens to all of them. And I'm not going to continue on this topic. I'm just going to say that it is natural for us to think about the space of a bunch of objects. But the objects today require a disclaimer. When I say curves, in my head, I think homotopy classes. And when we say homotopy class, what we really mean is that when we talk about two separate curves that happen to be homotopic, you can move one to the next one, then you think that they're the same. And when I think metrics on the surfaces, I think isotopy classes. And both of these sentences are things that, if you know, that's good. If you don't, it's also fine. Basically, we're talking about some ways to focus on what's different and what's the same. So let's just quickly give an example about the homotopy class. Is that if I draw the favorite food of some people, and then we say, oh, I have some type of curve, then that's kind of nice. And if I have another curve, that happens to be essentially the same curve but being moved about, then these two are in the same homotopy class. So we want to make some identifications regarding to what's going on over here. And then for the isotopy class of metrics, it's a little bit more to explain, so we'll talk about it once we get there. So where does the actual story start? Well, the story for today is to say there is some type of geometry going on when we talk about the space of curves. And the title has a bit of a lie in it because we didn't say a lot of things. It's not just geometry involved. In fact, today we're going to have geometry, topology, dynamical system, group theory, all wrapped up in one talk. So these four main things of curves and surfaces. So let's try to explain it first, just give like a quick introduction to what's going on. When we talk about geometry, I am not the hardcore geometer that would tell you to find the Riemannian metric or some type of cool sectional curvature of anything. What I mean by geometry is merely just we need metrics on objects and on the space of objects. So coming back to the little picture we drew over here, in two-dimensional space, we understand how to describe the distance between two lines. And in fact, we learned in high school that if they're not parallel, then the distance is 0. And if they're parallel, then there's like a neat formula using ABC to find the distance between two objects. But then you can upgrade it to talking about distance on the space of lines. You might say like the space of lines is something that's totally different from the xy plane, but you still want some type of metric. You want to say, how different is this line compared to this line in the R2 geometry. In the Euclidean geometry, these two lines intersect. The distance between them is 0. But if you have some way to imagine that this line can slowly rotate over to this one, and you imagine the lines are slowly changing from one to another, then maybe there is some way to give it a metric. So we need metrics on the space where we're staring at things, and we also need metrics on the space of things that we care about. But the problem is, it's hard to describe these space of objects if you have too many possibilities. So the topology comes in essentially to tell us about the equivalence relationships we want. So something like homotopy class, it's talking about, I have two curves, but I call them the same curve because really in the geometry, I plan to let their distance to be 0. The distance between these two curves happen to be 0. I'm just going to call them the same thing. The other thing that the topology is involved in is that these two curves are drawn here because this is a torus with topology. If I drew the curves on the sphere, then we might run into a different problem where every curve is of the same homotopy type. Every curve is the same homotopy class. Every single curve shrinks down to a single point. So that's a different problem for why we need the topology. So the topology also makes curves interesting. And then the dynamical system in the group theory part is kind of a setup for future stuff, but we can talk about the group theory very quickly. The reason why topics such as this, as simple as curves and surfaces, can still be something that a mathematician walks up to a colloquium and talk about for 60 minutes is really because that there's more to the story than just trying to draw fancy pictures and to try to talk about the distance between them. The group theory portion, there's the keyword called mapping class group, and if you are someone who doesn't need it, that's great. If you are someone who needs it, that's also great, but most likely it is not something you deal with all the time. And then for the dynamical system part, that's where we are trying to head to. So let's come back to something that we drew, but we can elaborate on. This is a torus. This is also a torus. If you spend some time in algebraic topology ever, or maybe just in general spend some time playing video games, then you understand that on the video game screen, on the computer screen, if something floats off to the top and comes back in from the bottom, or if something goes out to the right and then comes back from the left, then you are playing a video game on a torus. You are seeing something that's as simple as, oh yeah, you glue things together. So you glue the top and bottom together to get this, and then you glue these together to get a nice torus picture. And the reason why we change the way we draw the torus is because of something very, very unexpected. This is not a torus. Because this is something that's drawn on a two-dimensional blackboard, you are imagining that it's a torus. This is indeed a torus in every possible sense of mathematics because we defined how to glue things. And so we understand how to traverse this surface and in some sense, this picture gives a metric to the torus. So by drawing this picture, you can see that 2 points over here have a defined distance between them. Whereas if I draw 2 points here, first of all, you wouldn't know if my point is in the front or in the back. Then second of all, how would you define the distance between these 2 points? Do you travel around the hole in the middle or something like that? There's no hole over here. But the sad part is you can go in different directions. So you end up with kind of a different situation where the distance between your points are slightly awkward because there's different choices of paths. Maybe you just choose the shortest one, as people would usually do. Right, so we have a torus, and then we can talk about the space of curves on the torus. I call this the space of curves on the torus. And I should be a little bit more specific. This is the space of all geodesics and closed geodesics. On the torus with a flat metric. So there is something that we need to worry about, which is when I say this is a way to give some type of metric on the picture you were imagining. You might need a map to go between them so you actually can understand the metric over here better. And we were saying that if you draw this rectangle method, then you have a very, very specific metric on your space. And with the metric then you can talk about curves that go in a straight line, which is what geodesics was about. And one thing that I might not need to explain is that any point, if you go in a rational slope, you would end up getting a closed geodesic. So let's just give it some names. Maybe this is 0, 1. This is, that's 1, 0, and this is 0, 1. When you add those two together, the point in the middle is 1, 1. When you add these two together, you get 2, 1, 1, 2. These are the slopes of the geodesic. And the space of all curves that end up being pulled straight on the torus matches up with rational angles. So note, rational angles, the set of rational slopes. Describe the space. Describe the space of geodesics. Let's change the name to describe the space of closed curves. And there's a name to this as well. This is called the fairy graph. And people don't use the fairy graph for geometry. People use the fairy graph in number theory, actually, because it helps us look at continued fractions. So we will just say it like that, but not go any further. about that. If we want to think about closed curves on the torus, then there is something that you can imagine, which is that when you walk in a straight line on the representation that we chose to be the torus, you keep walking in the exact same slope, because every time you leave, you come back from somewhere else, and you actually keep walking in the same slope forever, giving the labels to which order we're moving. And if it's a rational slope, you come back to where you started. If it's an irrational slope, then you keep going forever. You're never going to come back to where you started. That's a very basic thing in number theory. That's also a very basic thing in dynamical system, where we try to imagine what's going on as you iterate some map. So let's get to what I promised. I promised to tell you the distance between two curves. And by the result, we should probably just say, yeah, it's of course obvious that you can define your own way of choosing the distance. You don't need to use the one we provide. We just want to provide one of them, being the curve complex. The curve complex was introduced quite a long time ago. But anyway, the curve complex is defined to be kind of a graph. Your vertices are closed curves, and your edges are pairs that intersect once. So this is a curve complex on the torus. We're going to update it to the curve complex of everything, but for now, on the torus, if you see two curves that intersect exactly once, so for example, the horizontal curve and the vertical curve and the slope 1 curve, these are all pairwise connected, and using the way of curve complex, you would just say the distance between alpha and beta is 1, because they are connected by an edge. Let's call this gamma, and the same goes for alpha gamma and alpha and beta gamma. But what if something has some other situation? So what's the slope here? Well, you have the good old method of looking at how many times it intersects the sides to tell you the slope is 3/2. And then you say, okay, maybe it's 2/3. Whatever. The slope tells you which point it corresponds to over here. For example, 2, 3 is this middle point right here. And maybe you would have noticed that this picture is the curve complex that we're drawing. This graph, when we are connecting things, we decided to connect exactly the ones that intersect once. Oh, maybe my coordinate is a little bit off. Let's focus on the top right corner. That is a little easier to focus on. So if you have a curve of slope described by 0, 1, if you have a curve that's slope described by 1, 2, then drawing them out, when you ask about how do you find the intersection between two curves of different slope, oh, you actually take the determinant of the 2x2 matrices, and you get the determinant is plus or minus 1. That's the rule for determining whether they are intersecting. And every point is going to have a lot of neighbors. So maybe You have to fill in the rest of the picture on your own, but the first thing is the degree is always infinity. Every curve has infinitely many other curves intersecting it exactly once. So there's this one that intersects alpha once. There's this one. There's also one that has slope 1/2. There's the one with slope 1/3, the slope with 1/4. All of these would have intersection with alpha exactly once. So the degree at every point is infinity, but the diameter, I should also say there's infinitely many vertices and edges. This is something that typical graph theory people would have trouble saying because they don't really like graphs that have infinitely many vertices and edges. And every point has infinitely many edges coming to it. And the diameter is also infinity. Despite the fact that every point has infinitely many neighbors, there are still points that are infinitely far apart. And so we should mention again this diameter, the distance between two curves is the graph distance. The smallest amount of edges you need to go through to reach another point. And that's where we can come back to the sentence we said earlier about if you want to go deeper and deeper and deeper, being further and further away from a point, you end up seeing something that goes to an irrational number via the continued fraction expansion. So if you take your favorite irrational number pi, decides to find its continued fraction expansion, which gives you a list of rational numbers that approaches it, then you end up seeing a sequence on the curve complex that is moving forward with no shortcut between the points. You are moving further and further away, guaranteed, when you follow along the continued fraction expansion.
Would you remind me what is the meaning of degree and the diameter here?
Oh, right. So the degree is the number of edges intersecting a point. So at every point, every vertex on the graph, it has infinitely many edges coming out of it. If the degree is 5, that means you only have 5 edges coming out.
Is it really graph theory? This is graph theory.
Yeah, the wording here, it uses the word complex, but it's actually graph theory. Right. And then the diameter is the shortest distance between the points. Sorry, the maximum of the distance between points. So you always end up having points that's even further away.
So in your definition, the distance between 1, 0 and 2, 1 is equal to 1. The distance between 1, 0 and 2, 1
Yes.
is 1.
Yes. And 1, 0 is this one, and 2, 1 is this one. So alpha and omega intersect exactly once. So it happens to be exactly here. So this is alpha, this is beta, gamma, and omega. So none of this is news. Basically, these are probably math that's done over 150 years ago, maybe even more. I bet these are at least 200 years old. But what people wanted to look at was the automorphism of surfaces. So they took a little quick change and say like, oh yeah, so why do we actually care about the distance between two curves? Why do we care about that? Well, there's a different storyline about an automorphism, or let's just make it more simply, a map from the torus to itself is, of course, determined by how it takes the curves and moves it about. So you can kind of use words to say it's determined by how it changes the curves or you can be very precise and say, I am looking at an isomorphism of my graph. I am looking for a map that takes this graph to itself that preserves edges, essentially. So also isomorphism of the curve graph, curve complex. I'll just use the curve graph because we haven't used it yet. And they use this isomorphism to explain what a complicated map would be and what a simple map would be. If you have some type of map on this graph, then you can iterate. So you have f acting on this thing, and then you just iterate f. You ask, what's going to happen? Well, it's going to be mapping things around to other curves, so maybe alpha goes somewhere else, and then beta goes somewhere else. If after some iteration you get the curves coming back to the starting point, then you have a finite order dynamical system type statement, or you have a finite order group element. But anyway, if your map turns out to be periodic, then that's the one that's not interesting. The only interesting maps are the ones that would keep going into places that's further and further away. And they call these maps the Anasoft maps. Or we can be a little bit precise and say every map from the torus to itself is a matrix. It's isotopic to a matrix, and the word isotopic came up. If you want to talk about how the square gets mapped to the square, and straight lines are mapped to straight lines, then you end up getting just a nice little matrix A, B, C, D. And the storyline in this approach says that the eigenvalues of this matrix tells you exactly the behavior of how it looks on the graph, how it looks on the picture, or what period the map would be. So that's one side of the story. Oh, by the way, this A, B, C, D are all integers, just to make sure that you have a nice map from the torus to itself. A lot of people would also add AD minus BC to be 1, just to make everything clear, but I'm just going to be a little bit lazy about it, right? The curve complex is not something that only lives on the torus, and as we said, torus is the age-old example that has been around forever. So we're going to stop thinking about it and just move on to more complicated objects. Because the same story works for more complicated objects. Any surface, closed surface, for people who haven't learned it, by the classification theorem of closed surfaces, you end up saying that it's called SG, a surface of genus G. Classified by G. And now everything becomes, once again, maybe worth saying. You still have closed curves on this closed surface, and you still have ways to talk about whether two curves are the same curve, and you still have a way to define which curves are adjacent or not. Oh, but this time the curve complex is a little bit slightly different because now we would mention that it's a complex. So quickly, we'll say vertices are edges. Vertices are closed curves. Edges are pairs that don't intersect. And then a simplicial complex when you have sets that's pairwise disjoint. But thankfully, those are formal words that we give. We don't need to worry too much. We're just going to say, right, there's once again a graph that is very, very complicated looking, that is once again defined to have the property that every curve is adjacent to infinitely many. If you want to, you can always go off to places where you are infinitely far away. I'm erasing some of these middle things. No, we don't need all of these. We don't need this as well. And we're going to add this third property where it might not be of meaning to a lot of people. The curve complex turns out to be something that's an object with a nice simple metric that comes from just nice graphs and everything. And this curve complex itself is a hyperbolic object. By hyperbolic, we mean all triangles are thin. So something about thin triangles. But that won't be the topic for today. Instead, we're going to move on to the topic for today. Right, so the curve complex, intuitive, easy to see, easy to define. What do we want to obtain from the curve complex? What we want to obtain is the boundary of the curve complex. Basically, the same question as we said earlier, that on the torus, you can keep going via continued fraction, go forever. What would you call a continued fraction approach on a surface that looks more complicated? How would you imagine curves that's getting further and further away? There's a single answer that says the curves seem to get longer as it nears. I guess near is in quotes because we don't have this defined. You can think about the curve complex, and because it turns out to be something hyperbolic, you can define the boundary via these rays that go off to infinity. And anything that's going close to the boundary must be getting longer, because if I find some curve that intersects alpha and beta, then I know that in order to go from alpha to gamma, I'll need to pass through some curve over here. So this omega happens to be intersecting with both alpha, beta, and gamma. And then if you want to find something that's not intersecting alpha, beta, gamma, and omega, then you need something that crosses all four of them. And in order to move further and further away, you have to look at curves that crosses more and more and more of them. Oh, I missed the word simple. I'm really sorry. On the torus, when we walk in geodesics, you will never have a chance to intersect yourself. But on more complicated surfaces, you are allowed to intersect yourself, and that breaks the story into two pieces. And that's the breaking point in 1980 when Thurston realized that, Thurston is just another famous mathematician, but when Thurston realized that simple closed curves kind of have a very important property, because something that doesn't intersect itself, but intersect others a lot of times, are supposedly very, very long. I have a cartoon prepared, which is something like this, becomes this, becomes this, and then becomes something that I have trouble drawing every time. Oh well. I don't know. Just draw something. So in 1980, also 40 years from now, a long time ago, something simple was discovered, saying that if you take 3 points, and what you do is you move this one over while you move this one over, then you get this picture, and then you move this one over, and this one over, then you get this picture. So people call this bread kneading. So if you've ever seen people making pastry, you take a piece of dough, flatten it, pull it out, bend it to the middle, then you pull it out again, then you bend it to the middle, and then you just keep on doing this. And the fact is, when you do this, what happens to a simple closed curve? It gets pulled around as you do this, and it gets very, very complicated. And Thurston realized that these curves are moving toward the boundary of the curve complex. When you move toward the boundary of the curve complex, two things are always happening. One is you are iterating one process, and the other thing is you are getting more and more complicated in terms of how you draw them. But drawing them is not the best way to do it, so we need to put metrics on the surface. So to make things precise now, we need a metric on this SG. So previously we said there's a torus. The torus has the picture that we drew, which is a square metric that is flat. And when you think about things, you can use the metric to define a lot of descriptions, especially the slope being something that comes out of it. We also saw that if your slope turns out to be a rational number, but very, very deep into the continued fraction world, then you end up with a curve that's very, very long. And we use the same concept on surfaces. That's more complicated to say, we're going to do the same thing. We also need some type of metric to make everything very precise. And so this comes back to the world, to the end of the 18th century, or maybe World War II. So we don't need the curve complex anymore. Instead, we need a quick story in hyperbolic geometry. And the key word is uniformization. If I look at a surface, a closed surface like that, if I put some metric on it, then you realize that there is such a thing called uniformize, where you can make the metric slowly turn into, or not slowly, depending on how you think about uniformization, you can say it's a magic box that takes a metric and turn it into a metric of constant curvature. So SG with metrics of constant curvature because of the topology, people realize that it's always a negative curvature. And when you go to the world of Riemannian geometry and come back, where then you say negative curvature corresponds to hyperbolic surfaces. So hyperbolic geometry Riemann surface is something that's already developed in the world of the end of the 19th century, which is done by Klein. So there's a lot of things that's already done by Felix Klein, the same Klein with the Klein bottle. And then in the World War II period, we have a different mathematician called Teichmüller. First of all, Teichmüller is a German mathematician who's actually a Nazi, and he died on the battlefield due to World War II, fighting for the wrong side. But that's a story for historians. But anyway, Teichmüller gave a metric, which is still to this day called the Teichmüller metric, between hyperbolic surfaces. So whenever we have some type of description of here's a surface, here's another one, then first of all, the picture means nothing on the blackboard. And second of all, if we just try to imagine these two surfaces having different metric, then maybe they would end up with a different hyperbolic metric after uniformization, because uniformization is a magic wand. And then you would ask yourself, if I have two different shapes, what's the distance between them? So some 70 years ago, actually 80 years ago, this is already done. And the description of distance, weirdly, finally takes us back to our flat surface. So we don't need this anymore. If I have some type of surface drawn out, if I have some other one that I call to be different, inside some type of things called conformal class, in its same conformal class, we have some flat metric. And maybe for this one, there is also some flat metric over there. So let's quickly say what is a flat metric on a surface. A flat surface, or a surface with a flat metric, is a surface with a chart, and then each piece of the chart is mapped to R2. And when you have transition maps, transitions are translations in R2. So someone realized that you can draw topological surfaces using polygons. that if you glue all the sides with some description, then you can understand that there is a topological surface sitting right here. This topological surface has genus 2 if you count the Euler characteristic. And when you can do a simple stretch to obtain a different shape, then you define the stretch map something like e to the k, e to the minus k, 0, 0. Then this k is called the distance, or actually, yeah, k is the distance that we were defined using this method. Right, so we didn't finish saying what we were saying in the middle. Let's try to do that. Anytime you get a surface, you can tell a story by putting metrics on the surface. You can choose whatever metric you like. There's a lot of different ways to put metrics onto something. Specifically, they say just use a lot of little charts on the surface to make a metric. But if you turn out to build something that looks like R2, that also moves like R2, everything looks like R2, then this statement guarantees a polygon. So the moment you have that description there, it guarantees that you have a polygon representation. And if your polygon representation is changing with a very simple map in R2, then you define the distance between these two to be k, which is the, I guess, the quasi-conformal constant. There's like a 2 involved that I'm not really worried about. And all of these stories are supposedly to lead back to now. So as a proper colloquium planning would be, now we talk about the futuristic stuff, or I guess the futuristic stuff for the people who worked on these topics. Space of these hyperbolic surfaces is a lot of times referred to as the Titular Space. So all the different types of hyperbolic surfaces of a fixed type. So somehow, even in genus 2, you get a 6-dimensional world that you can walk around in. When you walk around in that world, you can measure how far you have walked, and you can talk about how your shape is changing. The boundary of this space is something that's not as exotic as people would think. If you have some type of surface and your metric is breaking down, you're moving to the boundary, that means you're leaving the space, so that means your metric is somehow breaking down, then there is a pinching. So if you know what pinching is when your hole is getting closer and closer to the edge, and then eventually it breaks off right here. So we say that this curve pinched, and now we're at the boundary. And you ask yourself, what is the list of all possible ways that pinching can happen? And then you realize that it's exactly the space of the simple closed curves that we were talking about. So you can pinch along any curve, and that can happen, but there's a catch. You have to compactify it, or I'm just going to use the closure symbol on the board. And they gave this space a name, which one way to understand it is to think about the distance places. The boundary of the space of curves needs to be included. That when you walk along the curve graph, even the places that's far away, it's still part of the closure. And so one kind of description people gave is about using the length to describe this. So there's the alternative, a length description. Where they say, I'm going to measure the length of all the curves, and then I'm going to be able to tell if I am getting closer and closer to the boundary because I see something's length is going toward 0. So the length description is very, very nice and naive, and it led to some rigidity problems, asking about can we see this, quote, pinching from a finite set of points? If you've ever heard of the story about CAC asking about can we hear the shape of the drum, then maybe you know about this type of approach where you say, I'm going to take a geometric object, I'm going to measure some values, and then I'm going to ask, is it possible for me to just measure a few of the values to get the whole picture? And this is the moment when suddenly people realize that things aren't as they would hope for, because you have a nice storyline for the hyperbolic, but you don't have a nice storyline for the flat surface. So T of SG uses 9G minus 9 curves to do it. T of flat surfaces must use infinite So this is a theorem by my advisor and Kajra and Moon. But this is something in 2010. So sometimes closer to now. They realized, their result is this bottom one down here. The top one is by Klein once again, because Klein likes to do everything. So in the hyperbolic space, as we were trying to describe that thing, you don't need to see the one that's being pinched. You can just pick a fixed set of 9G minus 9 of them, and then you just observe what's going on to them to see if you're heading to the boundary. It can actually tell you which boundary point you're heading to as well. But if you change your storyline, you say, I have a surface, I'm going to put a metric on it, that's a flat metric, and we try to measure the length of curves on the flat metric. We try to say, well, this thing has length 1, this thing has length 2, maybe this thing over here has some length. Everything has a length. If I measure the length of every curve, it should give us some information. And the surprising fact that we don't get as much information as we need, and if we extend this a little bit to how do you make something slightly different but similar? You drill out the points. So you puncture the surface. So your surface supposedly now looks maybe something like this, with holes still in the middle, but also have holes in the other sense that extends off to infinity. So this is what I did in 2014, I guess. So you end up saying that in a flat surface, one of the things we didn't get to explain is how weird this corner point behaves. This corner is not just a normal point on the surface, it is a point with a cone singularity, a cone angle of 6 pi. If you walk around that point, you have to walk 3 circles, 180 degrees, sorry, 1080 degrees to take one tour around one single point. So if you puncture those, it's easier to obtain some control over those points, but you still end up with the fact that the length is not enough to determine things. Now, this length is not enough to determine things is not a new phenomenon, and I can leave an exercise for you. So the shape of the torus is not determined by finitely many curves in the L infinity norm. So if you're really bored, you can say, oh, I don't want to measure lengths by the Pythagorean theorem. Instead, I use the L infinity norm to measure lengths. And they somehow realize that you have this lack of understanding to the global picture because finitely many curves end up being something that can be easily squashed. So we never got to some of the further storylines, but that's where I will just kind of wrap up saying things like, the essence of the story is about simple closed curves are something full of a story to itself. And one specific interesting part is you try to find the compactification of this weird space, and you generate some type of new object to look at. And anyway, we'll just wrap it up there. Thanks for your attention. I'm sorry we didn't finish a lot of stuff, but we're fine with that, right?不用太紧张，我可以用中文回答。
说明一下这个刚才这个结果，说这个 space of hyperbolic surface 它的 boundary 就是对应到这个 space of simple closed curve， 就是譬如说用 G 等于1的情况，可不可以说明一下？在 G 等于1，我们可以很容易看出来为什么会这样的对应。
就是在 G 等于1的时候，我们可能的确应该要补上这一句，就是有一些人知道这个 moduli space， 也就是所有的 torus 的形状是长这个模样的，就是如果你今天试着要形容说所有可能的那个 torus 它的形状有哪一些，然后他们就发现说这个 moduli space 实际上是一个它是一个 fundamental region， 所以我们实际上所有的 torus 的形状组成应该是整个 upper half plane。然后你如果问说 upper half plane 如果我要走去无限远，要怎么样子走？那你希望建立的就是用 geodesic 的方式去靠近无穷远。然后 geodesic 的方式去靠近无穷远，就是先在这个 moduli space 上放 hyperbolic metric。然后你的 hyperbolic metric 的边界点就只有你的实数线，还有上面这个无穷远的那一个点。那他们就说你可以刚刚好把每一个点对应到的边界点想象成是你先画好那条曲线，然后接下来你就把那个曲线方向开始缩短，所以你的形状就开始变成这个形状。然后你的曲线就开始缩短，然后最后当你的曲线缩短到0的时候，你就到达了边界。然后这个 缩短的方法其实只跟斜率有关，跟它是不是封闭的没有关系。所以你随便一个斜率，你都可以从那个斜率的方向把它压缩到形状完全变成面积等于0，那一瞬间就是你的边界点。对。
那你那个 curve complex 的定义，为什么 G 等于1跟 G 大于1的情况是那个定义是不一样？那个 S 就 G 等于1，你说它是有交的话才画 H， 那为什么比较高的就是说 G 比较大，就是说是没有交才要画 H？
就其实是因为他们发现 Torus 没有不相交的曲线，然后所以他们才特地为了 Torus 去定义了一个新的版本。我们今天从那里开始讲，但是我们没有机会说那个相交于一次是因为在 Torus 上面任两条曲线都一定会相交，所以我们就取相交次数最少来当成是有没有边界。然后另外就是如果你用genus 更高的例子，然后你说不相交或者相交一次都连起来，你的 curve complex 的性质会一模一样。所以他们有不同的版本的 curve complex 是相交次数少于5次都连起来没关系，感觉起来会增加连通性，因为很多点都连在一起了。但是不管你连再多次，你只要是固定相交次数少于某个常数，你的整个图就一定会往外扩散，然后无穷远的点一定都是这一些比较难用肉眼看到，但是就是长度越来越长、越来越复杂的曲线。
有没有别的问题
？9级减6是什么算子 ？kernel 就是 co-kernel。9级减9是什么算子的 kernel 或者 co-kernel？
9G 减9是是一个凑出来的数字，它真正应该要的数字是6G 减6。然后他们的研究结果是说，如果我用6G 减6个曲线，你会剩下有限多个点，就是你的 dimension 可以用6G 减6消到只剩是 zero dimensional。然后它就是为了把最后有限多个点剔除掉，只剩的一个，所以选了很多个额外的。那6G 减6实际上就是曲线长度函数去看它的那个算 kernel 吗？算 kernel 吗？它的 pre-image。
6G 减6是可以离开的，但是下面的3G 减3为什么是这个数字？
对，就是当你说用6G 减6会得到finite 3G 减3个点，也就是说我有3G 减3个曲面，在那个6G 减6个函数上都有同样的值。然后他们那时候其实 Klein 那时候有提到说，6G 减6只要再加一个6G 减5就好了，就可以把那个有利的点找出来。但是如果你想要取一个，就是不需要先看到6G 减6个曲线就能够判别的方法，那你最好的方法是根据每一个 pair， 这边6G 减6每一组，你都要再去找第3个跟它们相交的曲线，就可以看到有那个 convexity 的条件。所以有3G 减3个是拿来对付一个凹向上的性质，凹向上函数会有2个点的值一样，然后它就是每一个凹向上函数去取一个方法删掉一个点。
这个3G减3是在 quotient mapping class group 之前还是之后？
这个要在 quotient 之前，对，就是其实在你 quotient 的 mapping class group 之后，你就没有曲线。就是你 quotient 完之后，你就不能说我在曲面上有一个曲线是长什么样子，因为 你现在就是这个曲线有 mapping class group 的 orbit 在，所以曲线长度在 quotient 之后也没有办法去讲清楚是什么意思，对啊，所以这都是在 quotient 之前，你的空间的确是有一个遥远的边界的模样，对。
所以这3个点都是 quotient 到同样一个点，
都是。这个句子比较难回答，因为 quotient 到同一个点这件事情是看你愿不愿意做那个 quotient 的动作，但是这里是完全选择不做 quotient 的，因为你一做 quotient， 所有的曲线都长一模一样，就是这条曲线跟那条曲线都可以用 mapping class group 连起来，所以所有的曲线都会长一模一样。对，所以这个我们 mapping class group 只提到一次，也是因为我们选择不要去对它做 quotient， 不要去讨论那个 modular space 的设定。抱歉，蛮糟的答案，就是逃避现实的回答方法。我们就是因为逃避现实，所以决定不那样做。
有没有别的问题？没有的话，我们就再次感谢傅老师今天的。